Welcome to the part 2 of the Defensive Programming in the Cloud series. In the first part, we talked about the retry logic. We looked at the storage library as an example. Then we also looked at how you would want to chaos test your retry logic, very important. And then we looked at the circuit breaker pattern. In this video, I'm going to talk about 3 other techniques for defensive programming techniques in the cloud. Let's get started. The first one that we want to talk about is paying close attention to the SLAs. So I have here the Redis cache SLA page, and you may know this already. Azure Redis cache offers you a 3 nines of SLA. So the availability, as you can see here, is available at least 99% of the times. While this may be fine because you may think that this is a cache service, and typically you would want to implement a cache aside pattern, which means that if the cache becomes temporarily unavailable, you should be able to go to the authoritative source of the data. So the 99.9 seems just fine. But what if you run into a situation where you or your organization may be using cache in a manner where cache aside pattern may not be applicable? You're probably storing, for latency reasons, you're storing some active state in cache, maybe a shopping cart or something like that, and you want it to be highly available. Now, keep in mind that Azure Redis Cache does offer you a high availability option where you have a master node and a slave node, and you can get higher availability. But even with that HA option, the guaranteed SLA is 99.9%. So what would you do in a situation like this? What kind of defensive programming technique can you use if indeed that Redis cache instance needs to be more highly available than 99% SLA? Well, one example that I want to show you is, let me bring up the Azure portal. One thing you can do is you can provision more than one cache, right? So in this case, you can see I've provisioned 2 Redis cache instances, and you'll see this theme sort of repeat itself later on in the talk as well. So I would then modify my program and make sure that I'm writing to both these cache instances. So when time comes to write to a cache, I write to both cache instances. And if for some reason one of the cache instance has a problem or a blip, then I can continue to go to the cache 2 instance and still read my data in that manner. Of course, it raises some questions that, who's going to be responsible for if one cache goes away and then you are now running on a single instance, what happens? You might have to, think through some possibilities there. Maybe you set an alert and you get notified that one of the cache instances is down, and you can maybe take an outage window and restart the cache and make sure both are in the same state. So that's one technique. I just want to quickly show you an example of this. Right? So here is a simple application that is going to simulate the behavior that I described. What we are going to do is the write operation is going to perform against cache 1 and cache 2. So let's start this. And you can see the write succeeded on the primary and secondary. So we are getting success here. And then I can also have a read operation that is going to read from one of the available caches, right? So it's going to read from the primary. And now if we go in here, and let's go back to the primary cache instance here. And then let's just try to reboot this cache here. And we just want to reboot the master instance. And let's just reboot this instance here. And if I go back to the program, and we will wait for it to reboot. So while it's rebooting here, let's just go back to our program. And now if I run it here, right now the reboot is still in progress, but you'll see at some point that the primary starts failing, but at the same time, we keep writing to the secondary, and then the read operation succeeds similarly. You can see that scroll past pretty quickly here. Let me stop this here. You can see if I go up to the top, you will see that at some point our primary started failing. I have to go all the way up to the top here. So you can see that the primary connection failed, but it was getting restored. But we didn't miss a beat here. We continued to write to the secondary. And if another thread came along and tried to read it, it would then skip the primary and then just read from the secondary. So this is just one example of how you can think about a defensive programming technique in this case, write to both the instances. Yes, it adds some more complexity, but then this is the requirement of the application where the availability of 99.9% is just not enough. Let's look at the next defensive programming technique. And in this case, we want to look at a condition where an uninitialized state, which can happen. Cloud is known for resilience, so things can get restarted automatically for you by the cloud provider. But you need to be very careful about paying attention to the recycle events and making sure that the state is uninitialized or initialized correctly. Let me show you a quick example. So this is a cloud service. Let me remove the breakpoint so you can see it better. This is a cloud service example, and this can apply in any other context. And in this case, as you know, when the cloud service gets started, an onStart method gets called, and typically you do a number of initialization steps there. And if those initialization steps tend to be long running, a common technique is that you initialize it once, and then once you've completed the initialization, maybe you write a breadcrumb to some sort of a persistent store. And once you've written it to a persistent store, there's a setting in cloud service where you can say you want that persistent store to be preserved across the recycle of that worker role instance. And this is a best practice, by the way. You don't want to directly mount a D drive or an E drive because that is subject to change. So in this case, we did follow the best practice there. We went to the local storage and we wrote out a breadcrumb file. And if that file was indeed present, we would check if the breadcrumb file was present. If it was indeed present, then we would skip these bulky initialization or expensive initialization steps. But this caused a problem because there was some sort of a disk failure. The worker role got recycled. Because we had the preserve local storage setting enabled, it came back up and showed us that the breadcrumb file was still in existence. And as a result, we came here and we said, if the breadcrumb file exists, then we were not going to do the registry instances. Now, in this case, what happens is, even though the local storage is preserved, the C drive that is powering the worker role has been switched, which means the registry has not been initialized. So this led to a problem, and the fix, of course, was that we also go in and check if the registry is initialized or not. If the breadcrumb files exist, then we don't do these initialization steps. But we also then go and check if the registry has been initialized. If that's been initialized or has not been initialized, then we go and set up the registry items here as well. So this is an important example to look at. Pay careful attention to what can happen under the covers. In this case, local storage was preserved, but the C drive got switched on us. And if we had not been checking for the registry, we would assume all of the initialization is in place and probably caused an outage. The last and final example that I want to talk about as part of this video is, once again, thinking about insulating your code against outages. And in this example, I want to consider a service bus example. So service bus by itself is not resilient across regions. However, one of the common patterns there is that you can use what is known as active replication. You can set up two queues in two different locations, and similar to our Redis cache example, when you're writing a message to one instance of the queue, you make sure that that message gets written to another queue in another region as well. You of course have to then worry about, now if your receiver is going to be reading from one queue, and if that queue becomes unavailable, the receiver can directly go to queue number 2 and continue to read these messages. Now it's important that you take care of duplicate messages, because you might have written 3 messages to queue 1, and then before you have read the third message, the queue 1 becomes unavailable. You go to queue 2 and you get message 1 and 2 again, and which you have already processed. So there has to be some sort of a duplicate detection mechanism built in for the scheme to work. Once again, similar to the complexity that was raised when you had 2 Redis cache instances and one of them went down. How do you reconcile the state between them? Similarly here, you would have to write some piece of code to detect duplicate messages, but the idea remains the same. Let's see that in action here. So here we are in the Azure portal, and I have 2 queues here, queue east and queue east 2, the 2 queues here. And let's just go to Visual Studio here. And I'm using C#.NET Core program. Let's look at this, the send active replication program. In this case, we connect to the primary and the secondary queue. And then what we do is we create a duplicate of this message. And then once we have a duplicate message, we send it both to the primary and secondary queue. So let's just go ahead and run this right here. And let me bring this window here. Let's just continue. And you will see that we have written 5 messages each, both to Q1 and Q2. And in fact, let's see if I can show this to you here. Let's just go into Q1 and you'll see that we have 5 messages here. And then let's just go to Q2 and you'll also see again that there are 5 messages. Okay, let's return to Visual Studio and try to run our receiver program. And the receiver program, to just make that our startup project here. If you look at the receiver program, once again, in this case, we are going to, this is the receiver program. And the only additional complexity here is that we check for duplicate messages and detect if we have already processed this message or not. So let's just go ahead and run our GeoReceiver program. Bring up the console window here. Let's continue to run. And you will see that we are getting these messages, except we've made sure that these messages are only getting processed once. So with this, we come to the end of video number 2. Here you saw 3 techniques. One was paying close attention to SLAs. If the SLA does not match your expectation or your client's expectation for a service, maybe you will need to write some additional code to make sure that you are insulating yourself against a possible outage. That will mean some additional plumbing on your side. So of course you have to do a cost-benefit analysis of whether that additional plumbing is worth this additional resilience requirement. We also looked at an interesting example of an uninitialized state. So in that case, a worker role got restarted. We were following the best practice of local storage, and we had set an option where local storage was preserved across recycle. And as a result, the breadcrumb state, which we wrote once we initialized the worker role, was preserved. However, the C drive of the worker role got switched, which means the registry got initialized, and that could have led into an inconsistency. So when you're thinking of optimization, thinking of initializing the state, thinking of when the recycle will happen, you need to carefully think through all the implications of a recycle event. Hope you found this useful. Thank you for watching.